Okay.
Hello everybody, my name is Omar, Alaoui, and today I'm going to present work that's been recently published in the ICRA Transactions on Medical Robotics and Bionics about the natural control of a lower limb exoskeleton and how upper body kinematics can be used to detect gait initiation intention in such a device. A little bit of background first. Today we are actually going to focus on medical lower limb exoskeletons, which have been emerging these last years for both assistance and rehabilitation purposes. For example, the Rewalk or Atalant exoskeleton that you can see on the left. However, one key aspect of such devices is that they should be perceived as extensions of the user's bodies, and to achieve such an integration, it is important to focus on control interfaces and how user motor intentions are conveyed to the device. By using the natural coordination that exists between different parts of the body during gait-related movements, such as the anticipatory postural adjustments or APAs that appear before heel-off during gait initiation, and pattern recognition techniques, it is possible to build control interfaces that feel natural and intuitive for the users. We conducted 2 experiments. In the first one, 10 participants wearing 3 IMUs, 2 on the arms and 1 on the back, performed 20 trials of 4-meter free walks. This was called the free setting. Data from the IMUs were then labeled according to 4 classes: no movement, gait initiation intention, right step, and left step, and were used in linear discriminant analysis classification architecture to build 3 classifiers for the second constraint setting, in which the participants climbed in the lower limb exoskeleton Atalant developed by the Wandercraft company and were asked to perform whatever upper body movements they thought would trigger the walking state of the robot. The 3 classifiers used for testing were the inter classifier, consisting of data from all participants but the tested one, the intra classifier, consisting of data during the FS condition from the tested participant, and the global classifier consisting of data from all participants during the FS condition. A second experiment allowed us to assess the robustness of such a classification architecture by adding an extra miscellaneous movements class consisting of recordings of everyday upper body movements such as coughing or reaching for an object, and this class was used to enrich the global classifier, and here you can see a 3D projection of the LDA generated subspace of such an enriched classifier. Results show that the global strategy adopted by the participants during the CS condition was to actively bring the upper body part contralateral to the standing leg forwards and toward this leg, as can be seen on the angular velocity signals shown here. Furthermore, the exhibited pattern was close to that exhibited by the subjects during the FS condition before heel-off, as can be seen on the example of the lateral acceleration on the right side here. The classification architecture performed well in detecting the gait initiation intention, or GII class, during the trials of all participants with low false positive and negative rates, as can be seen on the left bar plot, and the right bar plot shows that the inter and global classifiers performed better than the intra-classifier in retrieving the GII class, probably because of the richness of the training data. When testing the global classifier on the second experiment recordings, the false positive GII rates could be made lower by adding the MM class to this classifier, and testing this enriched version of it on the CS data showed that the GII class could be consistently detected in all trials but one. This video here shows how this global classifier enriched with the miscellaneous movements class behaves in an online setting. As you can see, the subject is performing different movements such as coughing and shaking hands, and the classifier correctly outputs that these are miscellaneous movements. However, when the participant intentionally exhibits movements to start walking, gait initiation is detected and the walking state of the robot is triggered. As a conclusion, this work shows that it is possible to build more natural and intuitive control interfaces for lower limb exoskeletons using generic and natural upper body movements. However, these results should be generalized and confirmed through the participation of more subjects and more trials. These Results can also be refined by assessing the evolution of strategies in time and the adaptation of subjects to false negative rates. The dimensionality of the classifier can also be reduced by properly analyzing the used features of the signals. And last but not least, the transferability of these methods should be assessed to impaired patients because they are the key target of medical lower limb exoskeletons and should be involved in future experiments. Thank you very much for your attention.
Okay, thank you. Well, we will now move on to the next video, who is by Joris from the Vrije Universiteit Brussel. And it's about the PROUD, a hybrid model-based learning approach for symbolic level robot programming by user demonstration. So here we go.
Programming industrial robots has a high cost because it requires a specialized engineer trained in using robot programming languages. With manufacturing these days shifting more towards customizable products in small volumes, there's a need to reduce this cost. With our PROUD project, we aim at reducing this cost by making the programming task more intuitive, replacing the engineer by cheaper factory workers. We wish to lower the bar to program a robot by creating an architecture that combines different robot components that help to make an abstraction of the programming languages. The PROUD architecture combines different components that aid in increasing the intuitiveness of the programming interface and reduce the complexity for the user, and to design a set of uniform protocols. We identified 4 components that can cooperate to shield the user from some of the programming complexity. In PROUD skill, we wish to improve programming of robotic skills that are robust against uncertainties in dynamic environments. A robot skill corresponds to a composition of robot behaviors needed to accomplish a task. The application developer designs the skill and decides which information is required to be modeled and learned. The application deployer uses the skill either by specifying parameters or performing demonstrations. A reactive constraint-based solver takes as input all this information and commands robot motions. The operator actively interacts with the robot application to fine-tune the parameters of the application. Here, parameters are required to define a skill are programmed by the user, but some of this information can be deduced from, for example, CAD drawings. In PROUD CAD module, we aim to leverage information in CAD data in order to reduce the complexity and improve intuitiveness in programming skills. To achieve this, PROUD CAD will allow users to augment CAD models with task-specific information, such as assembly constraints for 2 workpieces. The module will then process the CAD data along with this annotated information to automatically compose skills and generate some of their parameters. For example, composing force and torque constraints for a bag-and-hold assembly and deducing its assembly direction and applied insertion force. Model-based learning in this part is aimed at learning low-level skill parameters and recognizing high-level skill demonstrations. After leveraging information from, for example, CAD files, some optimizations are still required on parameters because of a mismatch between the model and the real system. This optimization will be based on a specific cost function of the skill and the task representation and task constraints. Attention will also be directed towards monitoring the learning process, including safety constraints, selecting appropriate parameter bounds, and representing the results in a transparent way that facilitates explaining them to the user. A model-free learning method will be used to generate assembly skill sequences based on human knowledge. An interactive reinforcement learning algorithm will combine knowledge interpreted from human advice given in natural language, together with knowledge that can be deduced from already programmed skills. For example, which skill sequences are physically possible. Since reinforcement learning requires a lot of episodes before convergence, it will use a simulated environment to speed up the learning phase. Lastly, up to this point, all knowledge went from human to robot. In Proud UI, we wish to look at a bidirectional user interface for improving human programming abilities. On the one hand, it will accept human knowledge in the form of natural spoken language and physical demonstrations as before, but on the other hand, will also let the robot explain its own behavior based on knowledge given by the user. A form of explainable AI in natural language that can help the user improve his programming abilities. To conclude, we wish to reduce the complexity of programming in order to reduce the high cost of reprogramming robots in a more customizable assembly in small volumes. By making interfaces more intuitive, less training will be required to work with these systems.
Okay, so moving on to the next presentation, and in the meantime, you can still type your questions for the past videos. So the next presentation is by Chunzhi from the Harbin Institute of Technology in China, and it's going to be about IMU-based motor intent decoding with full kinetics information.
Hello everyone, my name is Chunzhi, a research assistant from Harbin Institute of Technology. My topic today is IMU-based multi-intent decoding with full kinetics information. Okay, let's start.
The outline of this presentation is shown as follows. Firstly, locomotion plays a fundamental role in daily life. Under some scenarios, people might need assistance from robots to improve their mobility. Lower limb exoskeletons augment assisted joints by working collaboratively with users' movements and providing assistive force. The physically close collaboration therefore renders high importance on decoding human motor intent. The human motor intent decoding enables a customized determination of assistive force from four aspects, that is timing, magnitude, shape, and duration. According to different subsets of the four aspects, assistance with various subject-specific levels is applied to users by various exoskeletons. In this abstract, we propose an inertial measurement unit-based motor intent decoding scheme that can give full kinetics information in real time with stable signals as input. In this way, all the four aspects of the assistive force profile can be indicated with the subject-specific reference. Particularly, our potential contribution is that firstly, we construct a novel motor intent decoding scheme based on kinematics and kinetics estimation algorithms, which solely utilizes moves. Secondly, the assistive performance of a fully customized assistive force profile is planned to be studied by experimental validation of the algorithm. About our methodology, the workflow is shown in this figure. We firstly employed a sensor alignment-free method to calculate kinematics. Specifically, a biomechanical constraint based on the hinge joint assumption was adopted to estimate axes of biological lower limb joints. Another accelerometer-based constraint was used to estimate position vectors that describe the position relations of a moose relative to biological joints. Based on the estimated joint axis and position vectors, body fixed coordinate frames were built in order to transform the moose measurements into kinematics. Kinematics, including angular rate, angular acceleration, linear acceleration, and joint angles, can be calculated inside these coordinate frames. Secondly, a two-dimensional dynamic model consisted of 7 links were built to approximate human dynamics of locomotion in the sagittal plane. Kinematics was fed into the model to calculate joint moment in the sagittal plane. During single support phase, the ground reaction force and moment acting on the supporting leg can be easily calculated by the dynamic balance of each segment. However, during double support phase, the summations of GRFs and GRMs on 2 feet can be calculated following the same procedure, while the GRF and GRM acting on each foot was unknown. On this basis, The estimating method based on the smooth transition assumption was employed here to estimate the ratio of GRM and GRF on the supporting leg. The raption was calculated in a semi-empirical fashion as the function of the duration of support phase. Some initial results of the algorithm are presented in the slides. For kinematics calculation, red lines denote the reference curves from optical motion capture systems. Blue lines denote curves calculated from the algorithm. For kinetics calculation, red lines denote the curves averaged over calculated joint moment of the 5 subjects. Blue lines denote the curves of calculated joint moment of 1 subject. Black lines denote the reference curves of the same subject. The percentages on the figure denote the average RMSE relative to the magnitude of each curve. The calculated accuracy is the acceptable for controlling exoskeletons. Future work will include, firstly, improving robustness of kinematics calculation, because we observed that kinematics calculation significantly affects the final performance. Secondly, applying this motor intent decoding scheme on exoskeletons to demonstrate its feasibility and compare with the assistance determined by nominal joint moment curve.
I'd like to thank for the key research and development program of China for funding this work, and thank for Prof. Feng Jiang's supervision, and thank you for your attention.
All right, so the last presentation in this video session will be by Mathilde Legrand from Sorbonne University in France, and she will be talking about controlling robotic assistive devices with natural body compensation.
Hello everyone, I'm going to present you the work we're doing at ICRA with Mathilde.
Here we go.
I'm going to present you the work we're doing at ICRA with Mathilde and Modelbased, the control of robotic assistive devices with natural body compensations. First of all, appelling-assistive robots like robotic arm, exoskeletons, or prosthetic arms have nowadays a very well-advanced mechatronics. For example, all these devices are available on the market. They are FDA approved, but the assistance they can give is still limited because of their control, which remains a challenge. We propose here to analyze how the input signals of the control can influence the reaction of the user, because we think that this can explain why none of the current control schemes are fully appropriate. With a robotic assistive device, the user wants to reach a given target X with the end effector of the device. And this position X is a combination of the position of the body of the user and the position of the device. To position the device, the main approach used is what we call direct control approach, where there is a direct connection between an auxiliary signal and the motion of the device. The auxiliary signal can be electromyograms, electroencephalograms, and the motion of a functional human joint used as a joystick, like motions of the head or of the foot. You can see here that direct control approaches create two parallel loops, the control loop of the device and the control loop of the body. The thing is that these two control loops have different speed. The control of the body is much faster than the control of the device. And the user tends to prefer to use the control loop of the body instead of the control loop of the device. You can see here on this video a prosthetic user which first generates an auxiliary signal myoelectric here to move the prosthesis, but then he finishes the motion with his body because it's easier and faster. An alternative to direct control approaches is joint synergy-based approaches, where the relationship between the motions of two joints is modeled, and this model allows to control prosthetic joints with the motion of human joints. I have here the control scheme, where you see that there is no parallel loop because the input of the control comes directly from the motions of the body of the user. The problem is that the models are not fully accurate, so there is error that the user has to compensate, usually with body compensations. And the synergies depend on the task performed, which forces to have a complex algorithm structure with a first layer of classification that chooses the model to load to then move the prosthesis. Moreover, these two approaches, direct control and joint synergy based, are open loop for the device. You can see on the two control schemes that the only way to close the human-robot loop is with the human sensory system and usually visual feedback. If there is an error between the real position of the end effector of the device and the desired one, the only way to correct it is by the user with visual feedback. This is slow and cumbersome. And usually, it leads the user to use body compensations because it's easier to, instead of sending a new control input, he will just use his or her body, like the trunk or the shoulder, to compensate for the error of the device. What we propose is to close the control loop of the device by using these body compensations. So you have the control scheme here, and I just rotate it so that it's more visible. It works in 3 steps. First, we measure the posture of the user. We compare it to a reference non-compensatory posture. The difference between the current posture of the user and the reference posture gives us a position error of the device, which is then used to control the velocity of the device. This is natural, there is no learning, because body compensations are naturally used by the control central nervous system. This is versatile because the compensations do not depend on the task. And I just have to notice that it works for positioning and orientation of the end effector, but not for grasping, because there is no explicit compensations for grasping. There are 2 blocks we are currently working on: the mapping between the compensation of the user and the motion of the device, and the definition of the reference non-compensatory posture. What is it, and can it change across times? I will briefly present you the result of a feasibility study we performed with an upper limb amputee. This person performed a Rollion closed beam test with both elbow flexion extension and with pronosupination control with a proposed compensation-based control. We compared it to conventional myoelectric for prosthesis user, and you see that the task is performed in a faster time with the compensations-based control, with less mental burden for the user. The prosthetic joint use is increased, and the compensations are not much enhanced, even if they are used as input of the control. So you can see here on this video, on the left, the subject performing the task with myoelectric control, and on the right, the same task performed with the compensations-based control. To conclude, we propose a new concept using body compensations to close the control loop of robotic assistive devices for upper limb. It shows promising results with upper limb prosthesis. We are currently working on the theoretical proof of the human-robot system stability and on the control of more degrees of freedom simultaneously. And in future works, we would like to adapt this concept to the control of other assistive devices than upper limb prosthesis. So thank you for your attention, and I will be happy to answer your questions.
Thank you very much. So we will take the questions from if you have questions for all the attendees. So we do have one question first for Omar, a question by Fiona, and she's asking what methods or sensors are used to determine or measure the upper body kinematics.
Hello everybody, thank you for giving me the opportunity of presenting this work, and thank you for the question. For this work, we have been using 3 IMUs that were equipped with the triaxial gyroscopes and accelerometers, and these were placed on the back, on the upper back, and 2 other IMUs were placed on the right arm and the left arm at the biceps levels.
Okay, thank you very much. So we now have a question for Chunzhi, question by Erwin, and the question is, how does the method handle the initial position of the joints, and how does it deal with transients in the walking pattern, for example, when speeding up or starting or stopping?
Thanks for this question. It's a very detailed question. Okay, for the first part of this question, initial position, the initial position only affects the calculation of angles. Specifically, it's the angles calculated by the integration of angular rates. But for the angles calculated by the acceleration, it has no matter with or it has no relationship with the initial position. So when we fuse the angles calculated by acceleration and calculated by the integration of angular rates, it can be converged to the right value of the angles. And for the second part of this question about the patterns, in principle, our algorithm has no relationship with walking patterns or the transitions between patterns. But we just test our algorithm on the level walking. When speeding up or starting and stopping, there is no obvious deterioration of the calculations accuracy.
All right, so thank you very much. Now I actually have a question for Mathilde, and it's, so you're talking about non-compensatory posture. How do you define a non-compensatory posture, and is it something that's like user specific, or do you have like some kind of generic model there?
This is a tricky question, because it's actually the main problem of this approach is the definition of the non-compensatory posture. For the moment, we only worked with a task for which we know a kind of comfortable posture for the user, like being straight and with either sitting on a chair or just standing. But we're thinking of maybe building something that would recognize a comfortable posture. It could be either with kind of assessment tools like the ruler or something like that, or either something defined with each user, but it can depend on the task. For example, you can bend your trunk and it can be a compensation, but you can also be just bending your trunk to grab something on the floor, and it's not a compensation. So there's something here to work on to really define what is compensation, what is not compensation. So we're thinking to build a block of maybe machine learning or something like that to recognize easier the compensation or not.
Okay, thank you very much. And so one question for Joris now, which is more like a general question. I was wondering whether you had done already some user experiment on your different blocks, and like, or whether it's more like ongoing work. And if you had done some user testing, what were the results about them?
So yes, we started with one of the blocks with some user tests. That was the Proud Learn, where we wanted to learn assembly sequences based on human advice and natural language. And there we saw that it was faster for people to program it in less steps. And the system was also learning it quicker than doing like an exhaustive search of all possible assembly sequences, which was 3.5 million, let's say. So yeah, we got some positive results based compared to the general method.
Okay, so thank you very much.